Hello. This lecture will cover pages 9 through 17 of my lecture notes, so please print those pages out and have them in front of you as I present this lecture on Introductory Concepts, Part B, Digital Number Systems. If you take a look on page number 9, in your book, I think it's on page 14, I'm not sure what version book you're using, but we're looking at the decimal number system. I'm not going to spend any time on this because this is what you've been using since preschool. It has 10 symbols, 0 through 9. It has weight positions. The weight positions is based on base 10 system. Starts out with 10 to the 0, 10 to the 1. This is the units. This is the tenths. This is the hundredths. This is the 1/10. This is the 1/100ths, and so forth. If you have a 346, notice how the 346 is represented. I mean, you don't even think about this anymore, but if somebody pays you $346, it's really three separate transactions. They give you a $300 check, they give you a $40 check, and they give you a $6 check. Well, the reason we look at this decimal number system is because it relates directly to other number systems and how you use them. Look on page number 10. The binary number system. I'm going to give you a little convention here in my lecture notes. When you see 2 stars, I always tell the students this and they get a chuckle out of it, but I'll tell you it as well. When you see 2 stars, it means it's definitely going to be on a quiz or an exam. It helps you out a little bit. And if you see 1 star, well, it'll probably going to be on the exam. And if you don't see any stars, well, you just don't know for sure. Well, the truth of the matter is everything's important, but the 2 stars really will help you out. The binary number system has 2 symbols called bits, a 0 and a 1. And that 0 and a 1 could represent a lot of different things. In our course, the 0 is going to be represented by 0 volts ideally, and the 1 is going to represent 5 volts ideally. A bit, which you've heard about, you've heard the terminology a bit, it's a binary digit. It's an acronym for binary, B, digit, IT. And when you put 4 of these bits together, you get a nibble. And if you put 2 nibbles together, you get 8 bits, which is called a byte. And 1 or more bytes form a word. Okay? Now, why do I say 1 or more bytes form a word? Well, a nibble is a fixed number of bits, and a byte is a fixed number of bits, but a word isn't. A word depends upon whether you're in an 8-bit computer or a 16-bit computer or a 32-bit or more likely a 64-bit like you might have, 128-bit. We'll talk more about that in a minute, but 1 or more bytes form what they call a word. Here's the binary weight positions. Notice we have powers of 2 because it's binary. 2 to the 0, 2 to the 1, 2 to the 2. That's the binary point. And to the left, the powers are 0 through, in this case, 7, if we take it out a full byte. And to the right, we're going to take it out 3 digits, 2 to the minus 1, 1/2, 2 to the minus 2, 1/4, 2 to the minus 3, 1/8. Nobody memorizes these bit positions based on power. But everybody, there's 2 stars. Everybody that works in computers, in electrical engineering and digital engineering, memorizes these weight positions. So the sooner you memorize these weight positions, the better. Notice that anything to the 0 power is 1. So every number system has a 1 as a basic weight in the first LSB, the least significant bit position. But the weight positions are powers of 2. 1, you double it. 2, you double it. 4, you double it. 8, 16, 32, 64, 128. And it goes on, 256, 512, 1024, 2048, 4096. But, you know, I'll be happy if you just memorize it out 8 bits. And then to the right, 1/2, 1/4, and 1/8. So we're going to look on page number 11, and I want you to be able to convert each one of these. Convert this nibble, 0101, to a base 10 number. Well, if you take a look, 0101, if you write that in here, in the weight positions, we'll just do the nibble, 0101. What is that? I wrote real lightly here, but if you have a zero here, There you go. There you can see it. A 0, 1, 0, 1. Well, the weight positions are 4 and 1. 4 plus 1 is 5. So that's a 5 in decimal. That's a 5 in base 10. What about a 1, 0, 1, 0? Well, 1, 0, 1, 0, if you go back here, if you have the weight positions memorized, and you put in a 1, 0, 1, 0, you have a weight positions of 8 and 2, which is 10. This one obviously down here is 3 in base 10. How about this one here? Stop the video and do the rest of these. But let me show you something here on this one maybe real quick. Notice the weight positions here on this. We have a weight position of 128, we have 64, we have 32, we have 16, we have 8, and we have 4, and we have 2, and we have 1. That's our weight positions. And I have a 0, 0, 0, 1, 1, 0, 1, 0. Well, what's that represent in base 10? Well, it has a weight of 16, has a weight of 8, and has a weight of 2. That's 26. That's 26 in decimal. But I'm going to show you another way to look at this. Another way to look at it is, if you have these nibbles represented from 0, 0, 0, 0, the whole way down to 1, 1, 1, 1, that's 0 through 15. If you write these down and you get these memorized, and the quicker you do that, the better you're going to be in this course. Believe me, the better you're going to be. Write them all down and just memorize the patterns. So when you look at this and you see a 0, a 1, 0, 1, 0, you know that's the 10. If you see a 1, 1, 0, 0, you know that's the 12. If you see a 0, 1, 1, 1, you know that's the 7. Just have these memorized. You can look at this and you can say, well, there's 16, and that's 10. And there's your 26. You get the same thing, just you don't have to go through each power here. You can just take what this represents and just add it to what's over here. So if you take a look here at the rest of these, which is where we're at right here, let's look at page 11. Let's see if you got the same thing I did real quick. I'll show you how I do these, and then you look at them. It's going to take you a while. I've been doing this for a long time. If you look at this one right here, I see a weight here of 32 and 7. That's 39 in base 10. What about this? Well, that's a 15, and there's a 16. 15 and 16 is 31, and that's a 1/2. That's a 31.5. And this one down here, how easy is this one to do down here? Well, there's a 64, and there's a 16, that's 80, and there's 2, that's 82, and there's a 1/2, and there's a 1/4, it's 82.75 in base 10. Make sure you can do these for the quiz. The first quiz or the first mini exam coming up. You have to be able to do this, and memorizing these nibble patterns are a big part of it. What's the largest number that can be represented using 8 bits? So let's look at it right now and have this done the rest of your career. A 1111 1111, and notice I'm putting a space in here. I didn't mention that, but we want to make sure that when you show your 8 bits, when you show a full byte, I want you to make sure between the nibbles you keep a space. That's the professional way of doing it. Don't run your numbers together. You have 2 separate groups of 4. I did that here in all these examples. But when you have a 1111 1111, you can, in base 2, and you want to know what that is in base 10, you can add all those weights up, but I'll save you some time. It's 255 in base 10. You just memorize that, because you're going to use that many, many times this semester, and you're going to use it a lot in your careers. On page number 12, what I want you to do, stop the video, and I want you to show all the binary numbers from 0 to 28 using a full 8 bits. And I did it on Quattro paper, so take your time and write these in here. And when you're done, I want you to recognize something here. So maybe you ought to try this. Stop the video, try it, and then start the video back up, because this is what you should see. This least significant bit will change every time. Every one time it changes, it toggles back and forth. It's all powers of 2, the format of this. You go to the second bit, it'll change every 2 times. The third bit, it'll change every 4 times. This fourth bit will change every 8 times. The fifth bit is going to change every 16 times. You'll see a pattern there as you go from top to bottom on each of these digits, on each of these columns. On page number 13, typically in this course, a 0 logic level, ideally it's 0 volts, but anywhere from 0 volts to 0.8 volts is going to be a good 0 logic level. And logic level 1, we said ideal was 5 volts, but from 2 volts the whole way up to 5 volts, anywhere in that range, it's going to be a good logic level 1. So when we talk about ones and zeros coming up in the next couple chapters, which we will, a lot of ones and a lot of zeros. Zeros just represent a 0 voltage level, ideally. This is the actual range. And a 1 just represents 5 volts. Just keep that in mind. Here we have the number of bits, the number of states, and the largest number represented. So as you go through this, I want you to notice that n can be the number of bits. If you have 1 bit, you can only show 2 to the n states. You can only show 2 states. If n is 1, 2 to the n is 2. And you can count up to 2 to the n minus 1. If you have 2 bits, you have 4 states, you can count up to 3. If you have 3 bits, you have 8 states, you can count up to 7. Now what I mean is you go through this, is you'll see on another lecture, but real quick, if you just have 1 bit, x, it can take on a 0 or a 1. That's all the possibilities 1 bit can take. That's 2 states, and you can only count up to 1 because 0 is the first positive state. If you have 2 bits, x and y, what are all the possibilities there? A 0, 0, a 0, 1, a 1, 0, and a 1, 1. Notice with 2 bits, you can have 4 states. Well, there they are. 1, 2, 3, 4. And you can only count up to 3 because 0 is the first positive state. And do this for 3 bits, x, y, and z. And go from 0, 0, 0 the whole way down to 1, 1, 1. You'll see you'll have 8 states, but you can only count up to 7. So we have another lecture on this. I think the first lecture in chapter 2 talks about this, and I'll explain it a little bit more. On page number 14, I want you to know the difference between parallel and serial transmission. Real quick here, parallel, here's a computer, here's a printer. When you send something in parallel, you send all the bits together. If this is 8 bits, you send them all at the same time. Everything gets over there faster, but it costs more. Why? Because you need 8 transistors to drive each line here, and you need 8 receiving transistors to receive it on the printer side. So it takes more hardware, so it costs more. But serial transmission does 1 bit at a time. With serial transmission, just 1 line comes across here. And notice I showed you a bit pattern down here, sorta. The sequence as it flows. The start bit goes low. When this line goes low, it tells the printer it's a start bit. Here's a bit time, D1. Here's 2, 3, 4, 5, 6, 7. There's your 8 bits. They can be high or they can be low, depending upon what you're sending, ones and zeros, in what order. You have a parity bit, which we talked about, or we will talk about in a lecture coming up the next chapter. It's for error detection. It detects errors. That's what that parity bit's all about. Then you have 1 or 2 stop bits. When the line goes high, after you have a start bit and you have your data and you have the parity bit, sometimes you have 1 or 2 stop bits, usually 1 stop bit. When it goes high, the printer knows it received that character. The advantages here is it costs less because you only have 1 driving transistor and 1 receiving transistor. And the cable, the USB serial bus is very good on your computers, all that USB serial bus it operates like this. Now, I say it's relatively slow because it's one bit at a time, but that's a relative thing because nowadays these serial buses are a lot faster than what the parallel buses used to be years ago. But all things being equal, you can see that when you send something in parallel, in its nature, it has to be quicker because you're sending all 8 at one time as opposed to individually. And then page number 15, I just want to mention real quick the major parts of a digital computer. This is on page 15 of your lecture notes. It's in your textbook. Now, I want you to look at this dotted line. The arithmetic logic unit, which is the ALU, and the control unit, when you combine them, that's called a central processing unit, a CPU. And that line, well, that's in the microprocessor chip. Notice down here that the microprocessor and a CPU are equivalent to one another. And they are this control unit plus the ALU. And inside this microprocessor chip, or this CPU, there's an internal bus, there's a data bus that takes data between the arithmetic logic unit and the control unit. It can be 2 bits, it can be 4 bits, it can be 8 bits, it can be 32 bits, it can be 64 bits, it can be 128 bits. Well, that tells you what type of computer you have, whether you have a 32-bit computer or a 64-bit computer. So your home computer, if it's a 32-bit computer or a 64-bit computer, it's telling you that's the number of bits between the control unit and the ALU. You can't see this, it's inside the microprocessor chip. And then finally down here for your information, here's the equation that a microprocessor is equivalent to a CPU, which is the control unit plus the arithmetic logic unit. By the way, in about the 10th week, you'll design this arithmetic logic unit. You'll design this, and you'll say, it works. Wow, that stuff really works. But we have a ways to go before we get there. Here's a microcomputer. What's a microcomputer? A microcomputer is basically a microprocessor plus 3 other things. It's this microprocessor plus memory, plus input-output chips, plus support chips. These are 2 equations that I think will help you understand. I mean, who hasn't got confused with central processing unit, arithmetic logic unit, microprocessor, microcomputer? Well, if you look this over, it'll explain all that to you. And then the last page we're going to look at here in this lecture is small-scale integration, medium-scale integration. When we talk about small-scale and medium-scale integration, this is what we're going to be working with this semester, these 2 here. Small-scale integration is less than 12 gates in an IC, in an integrated circuit package. Medium-scale integration is greater than 12, but less than or equal to 99 gates in the integrated circuit package. And even though you don't know what ICs are, or what gates are right now, if you look down here, for general information, there are approximately 5 active devices per gate. And by active devices, I mean transistors. So just multiply these numbers by 5 if you want to know how many transistors we're talking about. But back through the 1970s, all they had is small-scale integration, medium-scale integration, and large-scale integration. That's all they had. But with today's technology and fabricating these integrated circuit chips, they're pushing the limits on what they can have. I mean, they're going over the limits on what they can have with transistors in small spaces using semiconductor physics. They have very large-scale integrated circuits now. They have ultra-large-scale integrated circuits now, and they have gigascale integrated circuits now. So that's what these abbreviations stand for. The homework for Chapter 1 is on page 17, and that concludes the lecture.